Alright, so in this reaction we are looking at a sample of S8. This is the last, one of the last two examples in section 16.3, and we are seeing what happens when it decomposes to S2. You're given the reaction S8 makes 4 S2s, and you're told what the initial pressure is, 1 atmosphere of S8, and the equilibrium partial pressure, 0.25 atmospheres. And so we're going to calculate the equilibrium constant for this reaction. First thing we're going to want to do is to write an equilibrium expression, so that would be S2 raised to the 4th over S8. And we're going to set up what's called an ice diagram, where we're going to see what happens as S8 transforms into S2. Ice is going to stand for initial change in equilibrium. You will be given any initial values that you need for doing these calculations. Since the only initial pressure we're given is for S8, we can assume that S2 was not present and therefore had a partial pressure of 0. We're also given the equilibrium partial pressure for S8 being 0.25 atmospheres. The initial plus the change should equal our equilibrium, and so we can figure out what that difference is, the change, by adding the initial and the change together to get that equilibrium value of 0.25. Stoichiometrically, the reason why it's just minus x is because there's only one S8 molecule in the balanced equation, while there are 4 S2 molecules being made for every one S8 molecule being consumed. So you will see the change for the S2s to be by a positive 4x. So this allows us to find the concentrations once the reaction has gone forward, or partial pressures, without having to do stoichiometry every time. So at equilibrium, the partial pressure of S8 is 0.25. With the initial pressure being 1, the difference between those would give us an x value of 0.75. So the changed S8 lost 0.75 atmospheres. That was then used to make S2. The reason we see that the reactant side is negative while the product side is positive, if you were going to calculate a reactant quotient, we would see that the Q value would be 0 since you had no products to begin with. In order to reach your K, or whatever the value is of K, you're going to have to make some products to force that reaction to go in the other direction. So we take that 0.75 atmospheres and we multiply it by 4 to account for the 4 S2 molecules being made, and that gives us a partial pressure at equilibrium of S2 of 3.0 atmospheres. When those two values are then substituted back into our equilibrium expression, we get that the equilibrium constant is 320, which means that the reaction favors the products to a large extent, and that makes sense with the equilibrium partial pressures that we determined. The last example in 16.4 is going to be dealing with concentrations. We have 4 moles of ammonia gas that's being placed into a 2-liter container at 388 Kelvin, and we're showing you that ammonia decomposes into nitrogen and hydrogen in an equilibrium reaction. And we're told how much ammonia remains at equilibrium. So it's the same type of problem that we just did, but we're going to calculate K this time as opposed to Kp. So first things first, we're going to write an equilibrium expression where the products are over the reactants. Remember that hydrogen is going to be cubed and ammonia squared based on the coefficients. Given our equation, we can figure out what the initial concentration as well as the equilibrium concentration of ammonia is by taking the moles and dividing it by the volume. So that gives us a 2 molar concentration for the ammonia initially and a 1 molar concentration at equilibrium. We do not have any nitrogen or hydrogen to begin with, so that tells us our reaction is going to have to shift towards our products, which means our reactants are going to decrease while our products are going to increase. Ammonia is going to decrease by a factor of 2x because of the 2 ammonias in the balanced equation, while nitrogen will increase by a factor of just x, and hydrogen by a factor of 3x. So if we keep in mind that the initial and the change should give us our equilibrium, 2 minus 2x equals 1, that should give us that x is going to be 0.5 molar. So nitrogen's concentration at equilibrium would just be the 0.5, while hydrogen's would be 3 times that, or 1.5 molar. Now that I have all of the equilibrium concentrations, I can solve for K by substituting those into my equilibrium expression. And when I get the math done with all of that, I get that the K is 1.7. So this reaction favors the products, but just slightly. So that should be the end of 16.4. And we're going to move on now to a little bit of 16.5. 16.5 is where we're actually going to solve problems with equilibrium. So far you were given equilibrium values or initial values and use those to calculate an equilibrium constant. Now we're going to give you equilibrium constants and have you use that to find some of those equilibrium concentrations without giving you any to begin with. We always want to make sure we start with a balanced equation, that we write out our equilibrium expression, identify any initial concentrations, get that ICE table set up, determine what our equilibrium concentrations should be, and then we will solve for them. And you can always verify your calculations by substituting them back into the K value expression and comparing it to the K that was given. So this problem here is a little bit more straightforward than the other two we're going to do. Hydrogen and iodine make two HI molecules. We're given the Kp at that 763 Kelvin, and we're giving you some partial pressures at equilibrium. We're telling you HI is at 4 atmospheres at equilibrium, and hydrogen is at 0.2, and we want to know what iodine is at. So we have given you two of the three substances and what their equilibrium partial pressures are, and we want to find what the third is. And since we have the equilibrium constant, we only have one unknown, so we should be able to solve for the missing one. Our Kp expression would be the pressure of our products over the pressure of our reactants. The products need to be squared since there's two HI molecules in the balanced equation. If we substitute in the the partial pressures that we have, 45.9 with our equilibrium constant, 4 for the partial pressure of HI, and 0.2 for the partial pressure of hydrogen, we should be able to solve for the pressure of iodine. Cross multiply, make sure you solve for the pressure of iodine and not 1 over the partial pressure of it. And when you do that, you should get 1.74 atmospheres. I think I ended up throwing this problem in this section just because of how your book assigned the problems were assigned in the text. This probably fit a little bit better in the previous section. These next two are going to be more along the lines of what I was talking about initially in this section. You're given an equilibrium constant, you're given a reaction, we want to calculate the concentrations for everything at equilibrium, and we're given that we had certain amounts of the reactants, but we don't have any of the products. The reactants were given to us in grams since we were told they were mixed in a 1 liter flask. So we need to get to molarity, which means we're going to have to change those grams into moles. We would do that using molar mass. We have a balanced equation, so we can go ahead and write our equilibrium expression, products over reactants. Once we have converted those grams into moles and divided them by 1 liter, we get that we have 0.055 molar of the H2O and 0.023 molar of the Cl₂O. We don't have any of the HOCl, so our reaction has to shift from reactants to products. The reactants are in a 1-to-1 stoichiometric ratio, so they're going to decrease by a factor of x, while our products are going to increase by a factor of 2x. So at equilibrium, our equilibrium concentrations would just be the initial plus the change for all three of those quantities. When you substitute those into your equilibrium expression and set your K to 0.090, that should be what your equilibrium expression would look like. This would be a quadratic formula type problem. To make your lives a little bit simpler, you can substitute in on your graphing calculators y1 equals 0.090, and then y2 would equal the expression to the right, and then graph those two sets of information and solve for the intersection. And when you do that on your calculators, be careful to put that whole denominator inside of one set of parentheses. You should get that x is 0.0045. I went ahead and did it out as a quadratic, but I know that takes a little bit of time, and there's lots of places where algebra could be have issues. So make sure that if you want to use the graphing calculator, that just make sure you substitute it in accurately. But once you get that x in terms of determining what the intersection is, you can substitute that back into your equilibrium concentrations and solve for what water would be, 0.051, dichlorine monoxide, 0.019, and because you had to double the HOCl, 9 times 10 to the negative third. Sorry, I had to go take a break and read for academic team. In the last example, if you take a look, you're going to see that the K value and what we ended up with for our final concentrations were pretty close to one another. And that was part of why we had to account for that X, then the equilibrium concentrations for the two reactants. What we're going to see in the next example is if there is a large enough difference between the equilibrium constant and those initial concentrations or partial pressures, we may not have to go through and solve for the quadratic formula. We may be able to assume that the difference between the initial and the equilibrium concentrations on the reactant side is minimal, and we use what's called basically a 5% rule to determine that. In this problem, because of how close they are, they're in the same decimal place, 0.09 to the hundredths, and 0.05, 0.02 for the reactant concentrations. That wasn't plausible. But in our last example, we're going to see that the K value is pretty small this time, 4 times 10 to the negative 7th, and we're dealing with concentrations that are in the tenths. So with that much of a disparity, I usually say if there's at least 2 powers of 10 difference between them, you're going to be able to make the math a little bit simpler. When your K is really small, remember that means that the reactants are favored. So N2O4 is going to be the predominant state that we see the molecules in, but there will be some NO2 being formed as well. In the experiment, we have 1 mole of N2O4 placed in the 10-liter vessel, and we want to figure out what the concentrations of N2O4 and NO2 are when equilibrium is achieved. So we have a balanced equation, so we can go ahead and write our equilibrium expression with NO2 being squared over N2O4, products over reactants. We can set up our ICE diagram. We know initially that we have 0.1 if you take 1 mole divided by 10 liters. We have 0.1 molar N2O4, and we do not have any of the NO2. So as a result, we're going to have to lose reactants to make products. N2O4 has a coefficient of 1, so its change is going to be by x, while the NO2 is increasing in concentration by a factor of 2x due to that coefficient of 2. So at equilibrium, technically N2O4 would be 0.1 minus x, and NO2 would have a concentration of 2x. Again, our concentration here is to the negative 1 power, while our K is to the negative 7th. That's a difference of 6 powers of 10. So we're talking about a pretty substantial difference between them. So when we substitute these into our equilibrium expression, we're going to go ahead and assume that that x that's after the 0.1 in the equilibrium concentration of N2O4 is negligible, that it's really not going to be big enough to make a difference in the concentration of N2O4 when equilibrium is achieved. So we multiply 2x, or we square 2x since that's in the equilibrium expression, but we're just going to divide this by 0.1. And I know that for some of you that are sticklers for math, that's going to seem a little strange. But hopefully when this is all done, it'll make sense why we were able to omit that x and not have to go through all the quadratic calculations for what's going to end up being a very minor impact on the whole problem. When we go through and solve this through algebraically, we're going to get that 4 times 10 to the negative 8th will equal 4x squared. Divide both sides by 4 and take the square root. And we get that x is 1 times 10 to the negative 4th. If you take 0.0001 away from 0.10, that's not going to change your answer. It's still going to be 0.1. And the 5% rule that we use is we take that x concentration and we divide it by the initial concentration. And as long as it is below 5% of that starting value, the assumption we made is a reasonable one to make. And I think when you do this one, you get that the percent error, or the percentage it was 0.1%. So that's really, really small. And it was a very logical assumption for us to make. Because we want to calculate the concentrations of the two components of our equilibrium mixture, we're going to substitute in that X value. N2O4's concentration will not change, but NO2's will be twice what is the X value, so 2 times 10 to the negative fourth. And this should be enough to get you through 16.4.